All right, good afternoon, everyone. So let's see if there's any questions. So someone says, my program is not exiting, it is still waiting for input from system.in. How can I fix that? That would be easier to know if I knew what that program was. So the program reads from system.in, and it reads a word at a time by calling in.next, I would assume. So it'll... Oh, why is my pen not working? Oh, here we go. So it calls in.next. W equals, and it simply has to be inside a loop that says while in.hasNext. And as long as you have a loop that says while in.hasNext, it's going to have to come to an end when the file comes to an end. Now, the only thing that occurs to me is now this. Maybe what this person was doing was trying it out on the command line, or for that matter, if you... So this is actually... now it's getting to be a good question. So when you have a program like that reads from standard input, and the way I'm going to run it is I'm going to run it on the command line. So, in fact, let me just do this real quick so that you see what I mean. Let's copy everything. Yeah. So I'm going to run Java, name of the thing, homework 7c, less than test.text. And then it's going to print the output like that. So when you take a file and you redirect, then it's easy to find what's the end of input. But let's say I just run it like this. Now the program sits here, waits for input, and so I can say and so I can keep giving it input. How does it know when I'm done? So unfortunately, typing in the magic phrase, hey, I'm done already, does not convince it. How about typing a blank line? That didn't work either. What's that? Yes, Control D. So in a Unix-like system, you hit Control D, and that ends the input, and now you get the output. So Control D is the magic key. And so that'll work in Linux, Unix, and Cygwin. And so you just need to know that Control D is that terminator. Why Control D? I have no idea. D for done. Now the sad thing is, if you do this in IDE, for some reason, the IDE vendors have not generally figured this stuff out. So in NetBeans, there's an enhancement request that's well over 10 years old to say that there should be some way of ending console input. And it's still not implemented. So for some reason, the IDE people don't really care about that. And that unfortunately means that when it comes to running such a program, you will need to run it on the command line for testing it. When you run it in the IDE, it doesn't really work. You could kind of work around that by having a kind of a second pathway in the program. Maybe you quit when you see the magic sentence, "Hey, I'm done already," hoping that that won't appear in the actual test. Yes? What's that? Well, you could, it'll return to the running program after each line, but the question is, how do you terminate the program? How do you terminate the input? So in the IDE you run, and I don't want to demo it here because then you'll see my solution. But in the IDE you will have this problem and you will not have a solution. There is no way in the IDEs, unfortunately, to, and I shouldn't say that so generally. I mean, I haven't really looked at whether Eclipse, it works right now. Yes?
Eclipse is Control-Z.
And Eclipse is Control-Z? Okay, maybe that's under Windows. Is it always?
That's under Windows. I'm not sure about Android.
Yes, because in the Windows console it's Control-Z, and so maybe in Eclipse it does work, and maybe they even adapt to the native convention. I have no idea whether it works on BlueJ, for example. I just happen to know that last I checked, NetBeans did not provide for that, and so that is a bit of an issue. What I usually do in that situation, I write my program so that if I run it with with arguments on the command line, like this, that it opens that as a file. Because when you open a scanner from a file, then when the file comes to an end, the scanner comes to an end. And that way I don't use the console at all. And then I just have to have a branch there that says, is args greater than 0? If so, read input from the specified file. Otherwise, read it from system.in. And that way you can make it work. But it's a bit of a hassle. Anyway, so the easy answer is for you to test it is use command line redirection. So use the less than test.txt or alice.txt, whatever you have, and that way it'll work fine. All right, so I guess that's what this question was actually after. So, and why does it pass NetBrat? Well, it passes NetBrat because NetBrat, of course, runs your program on the command line. Right? They're not actually an army of little NetBrats typing and stuff. It runs a script. All right. Moving on. Should the hash codes also be in sorted order? Yes, please. And the simple reason is, and it says so in the problem description, the simple reason is that way when I produce the expected output, I know exactly what to expect. If they could come in completely random order, it would be harder to make a tester. Since you know how to make the keys come out in sorted order by just using a tree map, just do that. It should be, if you haven't done it already, it should be a 4-letter change. Right, hash into tree, and the rest of your program shouldn't have to change. And here someone answered this one already. So if you have more questions about the homework, put them on so we can handle them after the lecture. Maybe this is an easy homework that people don't have a lot of questions. I don't know. You've got to ask. I have no idea which homeworks are easy for you and which ones aren't. Oops. So we're not doing lecture 19. All right, so now we're going to get into a new chapter. Again, that's in the PDF, not in the printed book. So don't bother looking at the printed book. Both chapters 16 and 17, we're taking the PDF, which has a few minor advantages. So we're going to be implementing linked lists. It's not actually difficult to implement linked lists we'll be walking through the code, and most of it is kind of going to make sense. But the devil is in the details, as you'll see when you actually make some modifications to this code. So let me draw the picture. I'm going to be drawing all the pictures instead of using the pictures from the book, because I want you to get into the habit of drawing those pictures yourselves. When you do any implementation with these linked data structures, it is very, very easy to misdirect some of the links. And so it's really important that you know exactly how they're supposed to be working, and the best way to do that is to start drawing them. So hopefully by seeing that I draw them, you'll find it a more natural thing too. So a linked list is some kind of an object that has it has a reference to the first node and that reference has that node has a reference to the next node. That one has a reference to the next node, and so on. And each of the nodes also carries a data item, which is a string, or in our case it's going to be a string just for simplicity. In general, it's just some arbitrary object of whatever type the linked list can hold. And we don't usually worry about the data too much. There's a few methods that read or change them. We're mostly going to be preoccupied with how these various links work. So keep in mind there's two kinds of classes. There's the linked list itself, which has a reference to the initial node, and then there's a whole bunch of nodes. Each of them has a reference to the next one. The very last one has a null reference in next, and that way one knows that one has reached the end of the linked list. There's also doubly linked lists where you have a reference going this chain of references going the other way around. We're going to be seeing those next Tuesday. So for today, everything is singly linked, just to make the code a little bit easier. So the node class is an inner class. That's just a convenience. That way we can keep the data public. The rest of the world doesn't get to use it, and we save ourselves a constructor and a getter and a setter. Saves a few lines of code. So let's come up with something simple first. We want to add an element at the head of the list. So let me change my color here to to blue. And so now I want to add a new node. So that node would need to be constructed. It has a next and a data item. So here it is, just completely naked. Nothing is in there right now. Of course, I'm going to have to fill the data item with whatever it is that that one wants to add, so some string. And now I need to link it into the existing scheme. So what I'm going to have to do is I'm going to have to change the links so that they look like this and like that. And that way it will automatically sever this link once I override it. So I would have to write code such as first equals new node and new node dot next equals, because this here is my new node. I should actually write that in my picture. New node dot next equals first dot next. No, equals first, because this one was first. Except I have to be very careful in which order I do that, because when I write first equals new node, then that already replaces the reference that was stored in here, and then I would not be able to find the node reference here. So I have to actually do this in the other way around. So I have to first set it this way, and then say first equals new node. And then the two references are updated. So let's see what code I have here. And sure enough, here you see that code here. I also have the code here that sets the data element. So that's kind of simple. What you have to be able to do is to draw this picture first with your own hands, and then from that picture see, oh, I have to reroute these two links, and then you have to be able to identify what those are. So I'll do it again in slow motion with the next picture that you see that. What happens if you misroute the links? If, God forbid, you did it the wrong way, say, then something somewhere is going to go wrong when one tries to traverse the linked list again. Let's say the mistake that I made is I said first equals new node, that sets this one, and then I said new node dot next. So the mistake that I was about to have made was would have created the links in this way. Now, if you ever make a mistake like that, then when you now iterate through this, when you just use a regular old iterator to iterate through this broken list, you're going to see the data item, let's say this was Fred, and then you're going to call next, and then you're going to see Fred again, and again, and again, because it's going to keep following the circular reference. It's an easy mistake to make, and it has the subtle consequences that happen much later. So one really has to be careful in updating these nodes entirely correctly. It's a difficult task, more difficult than you think at first. So let's remove the head, and again, let me draw the picture. So let me first get back to the picture without the first one added, so it's not so messy. So here's my node, and now I want to remove the first one. So that turns out to be actually very easy. All I have to do is make this thing point over here. And so the code is simply first equals first dot next. All right, so let me explain that. So I need to find a pointer that points to this thing, the target of my newfound blue arrow. That would be the same thing as the arrow that you see here. And so where is it? Well, it's in the next field, of which node? It's of the node that I can reach by starting from first. So it's first dot next. That's the arrow that I want to move, and I want to stuff it into the first slot. So that's the command that I need to make. And that's going to do it. What happens with this node here, the one that I've skipped over? Does it die? Does it get taken out and shot? Does it just sit there and mopes around? What happens with it? See, when we look at the code here, where you see this exactly the step, there's only a couple of extra pieces of code here that deal with, first of all, with the possibility that my list was empty, in which case it just throws an exception. You can't remove the head of an empty list. And then it deals with that we also want to return, because that's what the Java remove first method does. We want to return the value that was stored in the soon to be abandoned element. So those are these two lines here. But see, there's no command here that does anything with the node that's going to be abandoned. It simply is going to be abandoned, and eventually the garbage collector will notice that no one needs it anymore. And then it'll take it out to pasture and reclaim the memory. So how does the garbage collector know? Well, the only way that it was reachable before was from first, but now we overrode first to point to a different one. So there's no reference that points to it anymore. And so eventually it'll just be garbage collected. So when you want to remove something from one of these linked data structures, all you have to do is make sure that nothing points to it anymore, and it'll eventually go away. All right. Now, I just said here that this is really the primary action of the remove method to reroute that first link. And now I have this stuff here to remove this, to return the data that was stored there. So, but it's kind of funny that I'm surrounding that like this, that I have that I first get it and then I return it. It would seem to be simpler to instead here to just say return first dot data. Why don't I do that? That would have been a great clicker question. Very good. I already overwrote first. I replaced first with something else, and so at this point, first data is actually these data. And I don't want to return those. But as you can imagine, it's an easy mistake to make. You really have to keep the sequencing of these steps in your head and on a sketch of paper at all times, so that you really know in which order that you make that. That's why here I'm using colored lines. You might, if you just use it with a pencil, you might use dotted lines. In the book, you see how these steps are numbered with circle 1, circle 2, circle 3, just because these are kind of fairly intricate operations. All right, in the iterator class, just again to show how these things are implemented, I'm showing code for methods next, has next, remove, add, and set. I'm skipping a few methods that are not all that useful anyway. Moving backwards, well, we have a singly linked list, so you can't even move backwards. And the ones with the integer index are kind of bogus anyway. But I want you to see how the other ones work. Now, the biggest grief in all of this is the way that remove and set work in Java. So, if you recall, if you have a linked list and you want to remove something, let's say I want to remove the C, then what I have to do is I have to call next, next, next to jump over the C, and then I call remove, and a call to remove removes whatever it is that next had just returned, which really is kind of unintuitive. What you would kind of think is that remove, you would just move the cursor there and you would just kind of hit backspace like you would in a word processor. That's how it works in C++ and in every other system that I'm aware of. But in Java, they have this somewhat different way of doing remove, and it really is a pain to implement. So it adds really a certain amount of complexity to removal. And so, for example, I'm not allowed to call remove twice in a row. Whereas if you think of a word processor, of course you could hit the backspace key twice in a row. It would just remove two things. It's not allowed in Java. So I keep track of when I'm allowed to do remove in this Boolean variable is after next. Someone asked on Piazza some question about previous and position and remove. And in the book, in the printed book, I didn't have this Boolean variable. Instead, I used a trick where I used the relationship between these two other references, but people forever had a hard time understanding it. So I figured this time I'll make it very explicit. So, and I'll make sure that that Boolean variable in the iterator is after next is set to true when you're allowed to remove, namely right after you've done a next. And then when one calls remove, it'll check whether it's in fact true, and it'll turn it to false afterwards so that remove doesn't get called twice in a row. Now the other thing is, so the iterator keeps track of the current node. So an iterator might say, this is the current node, meaning the one that was just skipped over. And what is it called? It's called position. I'll call it pause here for lack of space. And the iterator also keeps track of the predecessor of that node, that I'll call previous here. That would be this one here. And it makes sure that previous is always 1 before the position. And the reason I have to do that is for removal. Because when I want to remove this node here, so let's say I want to get rid of this, what I have to do is I have to take this reference here and move it over to the one over here. And that means I have to be able to locate it. If I just knew where this node was, I wouldn't know where the predecessor's next reference is. So for removal, I have to find it, and therefore I have to remember it. If I had a doubly linked list, I wouldn't have to do that. Then I would be able to take the previous link of this one and find the predecessor, and we'll see that in the lab, I think around on Tuesday or maybe next Thursday. You're going to see how that simplifies the implementation a little bit. But for right now, where we have a singly linked list, I have to remember it. Now, strictly speaking, if I remember the predecessor, I wouldn't have to remember the current position, because I could always find it by following the predecessors next. And I was very tempted to do that, because it's nicer not to have to update so many pointers and not to have to keep them in sync. But there was just one teensy problem, and that was I had to figure out what to do when you are on the very first node. So right now my iterator points to the second node, but now let's say that I point to the first one. Then the position, of course, points here, and the predecessor, could it point here? No. Well, that would be another great clicker question. And the reason it can't is that these pointers here, when you look at the type, they are node pointers. They have to point to an object of type node. And so in the situation that you had before, this was my position and this was my predecessor. There's a node, that's a node. But now when I'm pointing at the very first one, it's a node, and the predecessor here, it's not a node. It's an object of type linked list. And so you can't put a linked list reference into a node variable. So what I do instead is I just say the predecessor is null. There is no predecessor. And so in this situation here, this is the only situation when I'm not able to recover the position from the predecessor. And only because of this particular situation that I have to be able to represent this position, am I forced to keep both the position and the predecessor. All right, so now let's see how we do a few iterator operations. And let me go back to this state here. So now I want to advance my iterator. So let me draw the picture. So afterwards, I want the position to point to the next one, whatever that is, and I want the previous one to point here. And I tell you, you have to do these drawings yourself. Just watching me draw is not really useful. You have to get out a sheet of paper and do that drawing with your own hand if you want to understand this. So let's work through the code. There is a bit of an exceptional situation where if I'm at the very end and then I throw this exception, you'll see in a minute why I have to do it this way. Now, the first thing I do is I remember the previous one. So that's actually pretty easy. The previous one is what the position used to be when you move forward. So that's what makes this red line here point to what used to be the further out green line. And now I have two different possibilities. It is possible that I was at the very, very big, that I hadn't even started moving anywhere, so that the iterator had pointed before the first position here. And in that case, both pos and prev are null. And then I'm making the position to point to the first one, which is here, and then previous is still null. So that's a bit of an abnormal situation. In the normal situation, I say position equals position.next. And that's the thing that makes position pointed here before, and now it follows the next field, and it now goes to this red line that goes further out. So, has next. Generally, I want to say has next is, well, how would I know whether, like this list here came to an end? So, and let's go back to this, to the situation here. How do I know there's something that comes after the second position? What I would have to do is I follow the position. Then I follow the next thing and I ask, is it null? That's the code here. follow the position, follow next, and check if it's null. There's only one nasty situation, that is when you are at the very beginning, when the iterator is conceptually here, then the position field is null itself, and if I were to call position.next, I would get a null pointer exception right then and there. So it's very, very common that you have these exceptional situations where, like, the very first position is represented by a null, and then you have to guard against that. And so generally, whenever I do some kind of a node pointer dot next or dot data, I'm so nervous about this that I always am on the lookout and say, how do I know it's not null? Because I've gotten so many of these exceptions when coding it up. You will too, and then at that point you will too learn to see, oh, there must always be a case for these things to be null. All right. Yeah, let's do remove. Why not? All right, let's say, so now I want to remove the element that's being pointed at. So that in this case would be this element here. So what do I need to do? I need to get this guy here to be moved over here. And that's all that I need to do in the linked list. But then I also need to worry about the iterator position. So let's say I have a list A, B, C. I just jumped over this one, and now I call remove. So conceptually at this point the iterator is here. And now when I call remove, what I expect is this situation. So that means I want the previous still point to where it pointed before, and I want the position to point to the next one. So let's see, previous.next equal position.next. That is the move that previous.next is position.next. That links out this one here. Position equals previous. Oh, I was wrong on what I said. So in this case here, I want the A to be the one that was just skipped over. So I'm totally wrong here. It's easy to fix. So I want my position to be here. And that's the line over here. I said is after next equals to false. I do that to make sure that I don't call remove twice in a row. And now I'm in a funny situation. When you look at this thing, previous and position point to the same value. They point to the same node. That seems so wrong. Now, fortunately, it doesn't matter, because the only reason that we needed previous was to be able to do remove. Right now, we aren't able to do remove because you can't do removes twice in a row. And secondly, there's nothing I can do about it, because I have no way of finding out the predecessor of this guy, because I don't have a backward link. It's not true that I have no way. I could start again at the beginning and loop through the entire thing and find it, but that would ruin my big O efficiency. So I have no easy way of finding out what's the backlink. So I'm just going to leave it in the slightly unsatisfactory state. The next call to next is going to disentangle previous and position again. But it really is a pretty subtle point. All right. So at this point, you must have your minds filled with this mind-numbing detail. and really, no one learns this stuff by lecturing. The only way you can learn to do these kinds of things is by implementing your own linked data structures and by really messing them up. So I hope to give you plenty of opportunity for that, and so that you get a feel for that. All right. So, but here is an exercise that you can do, and you'll almost certainly need a piece of paper. I don't think I could do this thing in my head. So let's say in this remove method, I change the first line here, this one here, where I'm throwing an exception. I simply say I just take it out. And I take out this line here, the is after next equals false. I just take it out. And now, at this point, I am able to call remove twice in a row, because this guard is gone, and the setting here is also gone. So I would be able to call next, and then remove again. And my question is, what would happen? So the way to attack that is to draw this diagram here. And now to really exercise exactly what the code does when you call remove the first time. And actually, give it one more node, because otherwise you're going to be running into this branch here. So, gosh, how can I do this? Let's add one more here. And now we want our iterator we want it to point here with the position, and we want the previous to point here. So when you take this picture and now try to call remove twice in a row and see what happens. Something unpleasant is going to happen. All right, let me set up the question in Piazza. Oh, that's a poll. So, previous next is position dot next. Previous next. Oh, that's this one. It's position dot next. Position equals previous. Okay. Now, previous next, previous next was position dot next. That doesn't change anything. Okay, so here's how I'm so far. So I said, let's assume that we're not on the first element, right? So in that case, previous next is position dot next. The first time around, that unlinks that element here. Then we do position equals previous. That now makes position and previous point to the same thing. Now we're going to do it again. Previous next equals position dot next. Well, but they're the same thing. Previous and position point to the same thing. So that doesn't change anything. That just assigns one thing to itself. And then position equals previous. Well, they're the same thing. They're still the same thing. So in this case, what have I achieved? I've called remove twice. The list has not been damaged, but only one element has been removed. So now what happens if I do it at the very first element? Because the question, suggested that might have a different outcome. So that would be the situation where get green. The position was this one, and the previous one was this one. So again, I skip over. So previous next is position dot next. That reroutes this link here. Then it sets position to previous. And now let's look at the code. And now it says if position is first, which is now the case, because now position points to the first one, then it calls remove first, which is a method that we've seen before. And remove first will just remove this element. So in this case here, I will have two elements removed. And I will have the iterator here point to an element that has been removed, which is actually, well, maybe not. It now sets position equals previous. Oh, that's bad, because that's still, it points to something that's removed. So let's see what the people's voice was 43. Yeah, no, so was option 3. Okay, so I managed to fool most people. So, and one more in the meantime. So it is wrong to say the second call to remove should have no effect. Stop adding votes to it. Because it only has no effect if you don't point to the initial one. If you point to the initial one, then the second call to remove will remove the initial one. All right, so everyone who's frowning, work this through again at home. And the way you can work it through is you have to draw the picture. It's not going to help you to look at my picture. You have to look at the picture. So what was the right answer? Well, I'll leave it to you to find out what's the right answer. One person had the right answer. All right. So Yeah, and sadly, 8 people said an exception would occur. Well, I guess maybe that's plausible. It could be a null pointer exception, right? That is mildly conceivable, but it wouldn't. All right. The point I want to make is that these are very intricate structures. If you make the slightest mistake, you get very bizarre effects that can be hard to understand. All right. Do I really want to do the code for the add method? No. You can work it out yourself. Instead, I want to talk about efficiency. So, in a linked list, in a singly linked list, if you want to access the 15th element, you have to skip over the first 14 of them in order to get to the 15th. So, to get to the nth element, you have to skip over the preceding elements. So, it's an O of n operation. It takes n times that skipping to get to the nth element. But now let's say you're already there. You are at the 15th element and you want to remove it. That removal is very fast because all that you have to do is you have to reroute a couple of links. So you don't want this one anymore. All you have to do is you have to move this link. Maybe a little bit of extra housekeeping. But it's only if it's a handful of operations, so it takes some constant time, or as we call it, O of 1. So O of 1 means it it takes a fixed amount of time. O of n means it's proportional to whatever n is. Now that's good because in an array list or in an array, if you wanted to take out an element here, remember you have to move all of these others back to fill out the gap. And on average, if the array has length n, that takes n over 2 steps. With a linked list, that is your big saving in the linked list. You don't have to move the other elements. Similarly with adding. So if you wanted to add an element here, you have to add 1 link, add 2 links, you're done. Constant time, very fast. So now there's a bit of a subtlety. What about adding at the beginning? Well, adding at the beginning is fast. You just move from you reroute the first link to a new one. that's a couple of edits, so that's constant time. What about adding the last element? Well, you would say, of course, I have to skip past all of the other elements to add at the last one. But that's just an implementation issue, maybe. Could we always remember a pointer both to the first and to the last? So let's play this through here real quick. So can I, in my linked list object, have first and last? That would, of course, mean that when I add a new element at the very end, I would need to update that pointer. That seems doable because I know whether I'm doing that. I can simply check whether I'm currently having my iterator point to the last one. When I remove the very last one, so let's say that now I want to remove this one here, then I would have to know the previous one. But that's okay, because how do you remove? The only way you can remove is if you have an iterator. The iterator would point here, and the iterator also knows the previous one, so I can recover the previous last. Or can I? Because here it says it's O of n. Yeah, I guess I'm going to have to look more carefully at that. No, I'm drawing a blank there right now. I'm going to... I'll pick her up again next time and do this a little bit more slowly. All right, and I think my time is up because I have a meeting in a couple of minutes, unfortunately, again. So we're going to dispense with the second clicker question. If someone... Yeah, we'll just dispense with it. And what I want to really quickly do is, there was a question on homework 8A here that I'll just do later. It's obviously not in a hurry yet. It's possible that there's a mistake in what's posted. Okay, yeah, we're definitely going to do this next time. There's a lot of intricacy in here. Let's look at the lab. So I know that a lot of people didn't get done with Lab 5, and we'll pick that up a little later. I want to get into Lab 6 because it contains stuff that's directly relevant to the homework, and I thought you would need that practice first. And so we will finish up the Mercurial thing so that everyone gets to experience how to deal with a shared repository, and I will make it so that in the future you get to submit stuff in there, but apparently that took a little longer than I thought. So in this lab here, you're going to get to implement some linked list methods, and it doesn't really much matter to me what those methods are. I really want you to be able to manipulate these links and to muck with them. So the ones that you're going to be implementing are pretty straightforward. They're not necessarily very useful, but there's one that gets the nth element, and there's one that sets it. But it gives you a good idea of how to manipulate these links. What's important to me is that you use these unit tests. I know many of you will have forgotten about the unit tests because they were 2 labs ago. So take all the time that you need to refresh your knowledge. My expectation is that you'll get to certainly through step A today, and maybe you get into B. That'll be great. And we'll just see how that goes when we pick it up again next Tuesday. All right.